to the end. Okay, so Anastasia, if you want to take it away.
Great. Thank you very much, Dan, for your introduction, and thank you very much to the organizers for inviting me. I'm very happy to tell you more about the work I'm doing. And as I said in the beginning, when I first received an invitation, I was like, are you sure you want to hear from me? Because I'm like very, very local redshift and not something what you would expect from cosmology seminar. But I see that you're open-minded and we can share things. So today I wanted to talk to you about the neutral hydrogen in life of galaxies, what we can learn by observing neutral hydrogen, and what are the future steps and perspective on the field. So to start, I heard that there will be students Q&A sessions. So to start mostly for students and to remind what neutral hydrogen is and how do we observe it. So basically it's atomic hydrogen, which consists of proton and electron, and when the relative spins changes from parallel to antiparallel, a photon is emitted, and the wavelength of the photon is 21 centimeter, and this is at zero frequency. And we can observe it with radio telescopes. And there are two different types of observations which we can do. One would be with the single dish radio telescope, as here shown on the left, which will basically give you those properties of neutral hydrogen in the form of a spectral line. So you see a typical spectral profile of a galaxy, and from this you can calculate the mass by integrating all the flux under this profile, or by measuring its width, you can calculate velocity with which the galaxy is rotating. You can go further than that and observe H1 with interferometer, and that way you will get not this sort of 1D information, but more a 3D information about your galaxy. So you will get spatially resolved distribution of H1, as well as the third axis, what we call 3D data, and you see it's rotating here, nicely visualized, would be the frequency, or converted to kilometers per second, the rotational velocity of the galaxy. And if you will collapse it along the velocity axis, you will get this thing which we call velocity field. And basically, you see the velocity gradient here, a simple Doppler shift. The red is rotating away from you, the blue is rotating towards you. And measuring the rotation velocity along the line of sight, we can basically trace the velocity of the galaxy as a function of radius. And this will become important when we study the gravitational potential of galaxies, how the matter is distributed, and rotation curves, and I will come to it later. So why, in general, the studies of neutral hydrogen are so important, and what we can learn about it? Basically, many things about the galaxies, their formation and evolution, as well as their life cycle, meaning how galaxies exhaust their gas and how they're replenished. For example, from galaxy structure kinematics, we can say a lot of things, measuring rotation curves and angular momentum of the galaxy. Also, for example, signatures of hot mode accretion are visible when you're observing the neutral hydrogen. You will see the anomalously rotating parts of the gas. You can trace outflows and the feedback. And of course, you can do large-scale statistics, for example, study its H1 mass function or velocity function. You can study how the spin and angular momentum of galaxy relates to its cosmic webs. You can even measure precise distances to galaxies, which are redshift independent. And of course, we always try to put things in the cosmic in the cosmological context to trace the cosmic evolution of these properties, like its omega H1, the global H1 density, is mass, H1 mass function is a function of redshift, and I will talk about it, but we are not there yet, but this is what we are aiming for. And this has a couple of the examples of how H1, when it is observed and imaged, looks. For example, this is a famous case of NGC 5055, and when you see the galaxy at its stellar body, you see that it is not very maybe interesting at a small stellar disk, but when you look at it in H1, you see that a lot of things are happening with this galaxy. It has enormously much bigger, larger extended H1 disks, which is warped. So already we can uncover the history of this galaxy, which we would not be able to see if we would look only at the stars. Here you see an example of the so-called ramp pressure stripping, meaning when galaxy is falling into the cluster, the gas is the first element to have a hit, it gets pre-processed, and here, since the galaxy falling into the cluster, probably this direction, H1 getting ramp pressure strips from the disk of the galaxy, so we already know what will be happening with this galaxy. The same example is M81 group, which is just a group of galaxies, and you would not know that they are so much connected, and there's a lot of things and bridges and tails and things going on between them. And one of the greatest example how hydrogen helps us to shed the light on something we thought is very dark. It's the example of a Leo P galaxy, which was first discovered in H1 and was almost assumed sort of dark, and only very deep photometry helped to uncover that there is some star formation going on, but it's extremely suppressed. And so the majority of its baryonic mass is in H1 in neutral form. And of course, elliptical galaxies don't have much H1, even though they have some, but mostly H1 is associated with the rotating and these galaxies. And in general, the structure of these galaxies can be described by just three parameters: their luminosity, radius, and their circular velocity. And all these parameters do correlate with each other for all galaxies types, with the tightest relation being between velocity and the luminosity of spiral galaxies. It's a simple linear correlation, but it became an extremely important in very different aspects of astronomy. It's called the Tully-Fisher relation. So first, what is the Tully-Fisher relation? It's a relation between luminosity and the rotational velocity of the galaxy. And first, it was discovered, it was used as a great tool to measure distance, the redshift independent distances to galaxies. For example, by observing with the single dish telescope, you can measure the width of the line profile, which will give you the information about the velocity. Then you can put it on some calibrated relation and you will get its total luminosity, subtract the apparent one, and you will arrive to the distance modulus. And this study is extremely important, and it's being carried on, and it's called cosmic flows, basically with intention to build the entire cosmic web of our neighborhood by measuring the peculiar velocities of the galaxies. Here I describe how they're measured, for which you need to know the distances. And by knowing the peculiar velocities, so the deviation of the Hubble flow of your galaxies, you can discover this large-scale structure and large-scale supercluster, for example, Vela supercluster or Laniakea supercluster, where we live now. So it was one of the first applications of the TFR. And first, of course, and then with the advent of the cosmological models, of the cosmological formation, of galaxy formation evolution, the models wanted to check, are they doing correct? And of course, scaling relations became one of the first tools, just to check that the reduced galaxies are realistic, they do follow normal scaling relations. And of course, nothing is easy from the first time. And you see here one of the first embodied simulations sort of prescribed baryonic physics. And you see here the Tully-Fisher relation and odd galaxies are offset from the simulations. And then it was understood that it is not so easy to produce realistic galaxies. And the Tully-Fisher relation is one of the greatest tools which basically can help you to have this sort of checks. And following many years later and up to now, all possible, I think in every cosmological model you can find it at Fire, Eagle, Illustris. Every suite will check their galaxies in compared to the observed Tully-Fisher relation. It's like, do they follow? Is everything correct? Also, semi-analytic models of galaxy formation evolution do check if everything works correctly. And everything does work, therefore, also alternative theories like MOND can check, are their predictions correct? And yes, you also see that the predictions will be correct. So now with the plethora of observed Tully-Fisher relations, every sort of model of galaxy formation evolution can calibrate to it, and everybody will be able to reproduce it. So at the end, we still don't know much why it holds and why it works. And I will talk a little bit about it later. And I was already mentioning to Dan, it's a bit hard to make just one line relation sort of super exciting. So that's why I always put this slide. It's an actual paper that Tully-Fisher is used a lot in SETI, in extragalactic SETI, basically saying that according to some calculations and simulations, the outliers of infrared Tully-Fisher relation can be the hosts of type 2 civilizations. So I always try to put this slide just for entertainment. So the development of the two axes of the TFR, it was happening simultaneously, but pretty much independently. First is the luminosity was first measured from photographic weights in B band, the scatter was very large. And then slowly with the advent of the technology, it was understood that the space-based near-infrared photometry, like for example 3.6 micron, will give the smallest scatter on the TFR, basically because it traces the all-star population, which build up the bulk of the total baryonic mass. And therefore, it was understood that if we include also gas mass on the relation, then the relation should be tight and hold better. And this is where the nature of the TFR started to become uncovered, that it must be the relation between the baryonic content of a galaxy, which is traced by its total baryonic mass, and by the dark matter halo of a galaxy, which is traced by the galaxy's rotation. And this extremely tight scatter still, which basically measured to be zero, still puts a great question to the lambda CDM models. So because they still account for some scatter in the halo mass and the baryonic mass inside it. For the rotational rate, also things were progressing, as I showed in the beginning. First, there was just one measure taking for the whole galaxy, the width of the W50 profile, which relates to the rotational velocity of the galaxy if it's corrected for inclination. But of course, with the interferometry, as I showed, we can measure the rotation curve of the entire galaxy as a function of radius. And with H1 disk being so much more extending than stellar disk, you can see that H1 disk can trace much further into the dark matter halo potential. And indeed, the famous decomposition of the rotation curves when you account for your gas and stars, and you see that there is still needed matter to build up the observed rotation curve. That was understood that it must trade the dark matter potential, and that was one of the first evidences, observational evidences for the dark matter in galaxy. And this is, I just put an example of how W50 can relate to the rotational velocity measured from the rotation curve, because of course rotation curves, they're not like flat and featureless, they have bumps, and usually V flat. So the part where flat part of the rotation curve reaches this flat part, it's considered the one which is tracing the dark matter halo the best. But often, for example, flat part can be below the V maximum for some very massive galaxies. But in general, you might hear V flat, V max, or V out. It's all the rotational velocity measured at the outskirts of H1 disks in the faraway radius from the rotation curve. So at the Tully-Fisher redshift 0, we know probably everything we could possibly know nowadays. We know that it holds in every wavelength range, with the scatter disk decreasing, indeed decreasing in the infrared bands, which is supposed to trace the total baryonic mass better. We know that it holds for all the different velocity measures, W50s, which is much easier to measure, to the rotation curves and different values derived from the rotation curves. And we know, and for example, when you have your photometry and the W50 relation, you can apply it to measure the distances to your galaxies, because then the vertical scatter is what you care about. And and you can calibrate with existing different distances, and you can measure W50s for much bigger amount of galaxies than UV flat. But when you go sort of into study the observed Tully-Fisher relation, which will suit for tests for cosmological models and predictions, then of course you want to do it for the baryonic mass, and you want to use the velocity derived from the outermost flat part of the rotation curve, which traces your dark matter potential. And what you really care about is the tightness of your relation, or the perpendicular scatter, because lambda CDM does not allow for the zero tightness of the relation. It still wants you to have some flexibility, while the observed relation now, it's almost agreed that it has much smaller or even zero intrinsic scatter. This is what we know about Tully-Fisher relation at redshift 0, probably everything. So we will leave it a little bit for now and move to the small scale challenges to lambda CDM. As I said, Tully-Fisher itself did place some challenges and still does, but studying the kinematics of galaxies, and in particular small galaxies, and studying the H1 context helped to put like even more challenges and to discover more challenges to lambda CDM and this completely small scale. And here are the problems listed. One of them is the missing satellite problem, because the simulation predict that there should be many more satellites than what we observe, for example, in the Milky Way. Another one is cusp versus core. As I already mentioned before, you can decompose your rotation curve for the contribution of different components, gas and stars, and then still there would be a lot of matter which is not accounted for, which is supposed to be addressed to the dark matter. And cusp versus core arises from the problem that lambda CDM usually uses NFW profiles, which are extremely cuspy for all galaxies, while dwarf galaxies, looking at their rotation curves, were found to have chord profiles. And then there is a planes of satellites, which I will be not talking about, but it's basically was observed that many central galaxies do have aligned kinematics of all their satellite galaxies. And one of the most interesting, to my opinion, and I'm biased because I did work on it, is the too big to fail problem, which is combining in itself the missing satellite problem, so too many satellites in simulations, too few we actually see in observations, and the cusp core problem, where the internal kinematics of dwarfs does not actually correspond to the halos where they're supposed to live. Oh, excuse me. So first, it was noticed in the Milky Way that if you see here, for example, on the left, you have a central halo. It's a dark matter only, have a central halo and a lot of little satellite halos. And you can basically choose and pick which one will be living inside the Milky Way and Milky Way satellites. But given the low number of observed Milky Way satellites, it means that the galaxies should be forming only in very restricted number of these halo satellites. So what does it mean? And that means that's like our galaxy, Milky Way, or any other central galaxy should have a lot of dark matter halos which will be empty, meaning that they fail to form galaxies. But it would mean that you would pick up the bigger one and trace the kinematic. You would think that the bigger subhalos did form galaxies and small ones didn't. However, and how can you prove it? You can look at the kinematics of your observed satellites and basically relate your V out or V of rotation curve of V max to the potential of the dark matter halo and therefore to its mass. And then you can measure from simulations the rotational velocity of the halos where you want them to live, and you see they're in a big mismatch. And it means that if our kinematics does trace the halos where a galaxy lives, then many more galaxies live in much smaller halos, and there should be a lot of big empty halos, and this is where the name's coming from. They are too big to fail to form a galaxy. so this like big mismatch of the number of them, and that only small halos supposed to have galaxies and big ones would be just empty, is one of like the big challenges. And of course, many solutions were proposed on how to solve this problem. And one of them was that the mass of the Milky Way is probably too low, or that the Milky Way is just an outlier in terms of subhalos, and it is a very special system, and we will not see it anywhere else. But and of course, different studies looked at M31 satellites and at the local group satellites, and even at the local volume. And you see that all these galaxies, they're just basically too small. They rotate not fast enough to live in those halos. So this problem did exist even there. So another solution was proposed for the using Ni-Hao simulation suite. It's basically, say, stellar feedback creates chord profiles in dwarfs. And as soon as we resolve this problem of core-cast problem, and now simulations are able to simulate galaxies with chord profiles, too big to fail will be soon automatically. And here, if you look on the left, for this sample of galaxies with using stellar and H1 kinematics, which is not very extended, not like both 1.5 kiloparsec, where you can trace your rotation and your rotational velocity in your rotation curve, you can see that observations do align with the rotational velocities of the dark matter halos. So the problem was thought to be solved, and that is the case. However, if you again will go just to H1 sample, and you would select only those galaxies with extended H1 disks, which probe much further into the halo of a galaxy at much larger radius, like you see here, again, the problem will stay, and the kinematics basically here, galaxies will flatten out, they will not rise, and again, the kinematics of the halos and the galaxies stays mismatched. And another solution which was proposed quite recently, and I think now it became like one of the more stable ones, is basically to say observed H1 rotation curves do not trace the true potential of the dwarf galaxies at this regime. Because if you look at the observed galaxy from little things here, its velocity field is extremely messy. So how can you talk much about the regular rotation when there is like a lot of things going on? And this is its stellar counterpart, so you also cannot say much. And we performed these studies where we used the Moria suite of zoom-in dwarf simulations, and then we observed it with the radio telescope, pretending that this is how we would observe it. And we created data cubes and used pure observational techniques to derive the rotational velocity of the galaxy. And here you see that in blue is the derived rotational velocity, and this is the velocity of the halo. So even from the simulations, you will get this sort of mismatch, which suggested that maybe observations all along were not tracing the actual true potential of the galaxy. And it was also confirmed for apostal hydrodynamical simulations, but it's still a debatable matter and should be addressed, because the whole solution should be applicable in any environment, and also be applicable to dwarfs to which you can trace kinematics correctly, and to all different masses. It should be working outside the core radius, and of course explain the problem in stellar kinematics and H1 kinematics. So it is still an open question, and in general dwarfs like create a lot of problems for this very small scales of lambda CDM. So this is like where we stand now in terms of H1 kinematics for galaxies and different scaling relations and their kinematics, which we can address. But what is the future of H1 studies? Where we can go from now, how we can improve and study things further away, and maybe the evolution. The problem is that H1 is extremely faint. You need very long integration times. You need very high sensitivity to detect it. And on top of that, together with sensitivity, you need very high resolution to be able to measure the resolved kinematics of galaxies. Therefore, for now, H1 observation is just limited to a very local universe. And I know Natasha Maddox was giving a talk here months ago, and she already mentioned surveys like Chiles and surveys like Alpha Alpha, who are basically the latest state of the art. And for example, Chiles is a VLA survey on the cosmos field. It managed to detect one galaxy at 0.3, but with integrating on 178 hours. So it's not very sustainable. And of course, there are tons of technical limitations, starting from the whole band of the redshift from 0.1 to 0.2 affected by RFI. And therefore, since we couldn't do much in H1 now, of course, there were many attempts to try to build up and study the evolution of the Tully-Fisher relation above zero using different kinematic tracers. For example, CO was used on one of the kinematic tracer, and then the conclusion was that there is no evolution of the TFR up to redshift 0.3. But then the optical lines like H alpha or 3 were used to study it, and it found evolution all the way from 0 to 1.3 and further. Another study, which was using optical lines again as a kinematic tracer, found that there is no evolution of the slope, but only evolution of the 0 point. So basically, different lines and different tracers will give you different answers, because it is not a systematic study which you compare to the systematic study at redshift 0. So what you would want is one survey which covers it all from redshift 0 all the way to the highest redshift, where you can deal, which you can treat exactly with the same techniques and in the same manner to study it. And hopefully we're living in extremely exciting times to do this sort of research, any sort of research, I think, in the radio. And this is like the pathfinders to the SK facilities. And one of them is Meerkat. It's a great instrument. And again, Natasha mentioned it a lot in her talk, so I hope you all attended and you know about it. But just to give you a small overview, that one of the surveys currently being conducted with Meerkat is called Mighty survey, and it's commensal in H1 line and in continuum. So I will be focusing more about H1 line, and basically it will detect this amount of galaxies as of this H1 mass as a function of redshift all the way to 0.4. And it's commensal with another survey, Laduma, which will go much narrower field, but much deeper. So we finally will be able to push H1 studies below local universe all the way to redshift 0.5, 0.6. And this is happening just now. So we are extremely excited to work in this field. And we have our Mighty H1 early science results, which again, Natasha already mentioned. But just to remind you that we have around like 280 H1 detection in this redshift range. So basically the 0.083. So it's last 1 billion years, which we can probe in H1. And we have measured its H1 mass and its stellar mass. And we see that they are all aligned with Alpha Alpha survey. So we know that our values should be great. And what do we do next? We have mass of the gas, we have mass of the stars. Let's try to measure its velocities. And we try to measure velocities in 2 different ways, as I already mentioned, using the W50 or just one number for entire galaxy. It was our first attempt, but we have a huge caveat, is that our velocity resolution of the early science data is extremely poor. It's like 44 kilometers per second. It will mean that any galaxy which is a dwarf of 40 kilometers per second will be simply missed within the channel. Therefore, in order to be able to measure precisely or better, we employ new techniques. Of course, new telescope, new techniques, we always need to check this sort of things. We employ new techniques of fitting a busy function combined with the Bayesian tool, which basically will show us all the possible outcomes of the W50s, and which we will be sure that they will be measured to the best we can, even with this very sparse velocity resolution. And here is the comparison of the W50s we measured as a function of H1 in comparison to alpha survey and MIT survey, and we are doing pretty nice. And of course, another caveat, always when you measure the velocities of rotating galaxies, you always need to correct for geometry. You need to correct for inclination, because your galaxy is in phase on its rotational profile will just look like a Gaussian and not as a nice double horn profile if it's 90 degrees. So we always need to know our inclinations to be sure that our velocity is measured correctly. And that's why we're extremely lucky, because MIT has great wealth of ancillary data, so we can measure our inclinations and from the optical images and from the H1 maps, and they're extremely consistent with each other, if you can see here. So we can assume that we can measure our rotational velocities pretty well, even with such velocity resolution. And our next attempt, of course, is to go further and to try to measure their resolved kinematics and to measure the rotation curves of these galaxies to see how they react, how, for example, they relate to W50s at this redshift, because it was never done before beyond redshift 0. And in general, can we do it, and how rotation curves will look like? And of course, there are many caveats here as well, because as I said, for this, you should not only have good velocity resolution, which is already bad for our case, it's 44 kilometers per second, but you also need to have pretty good spatial resolution. And we have galaxies like this one, where it's just 28 beams across, so we can get a nice rotation curve along it. And here you see approaching and receding side of the galaxy. It's something what we call position velocity diagram. But the majority of our galaxies look like this. And of course, again, we need to think of the new techniques and new ideas how to measure its kinematics, and the development of new software techniques arise, because before, for example, we needed to know everything in advance for this galaxy to suggest to our software what will be our systemic velocity, what will be the position of our galaxy. Finally, now we can do it all automatically, and the current software requires just 3 to 2.5 beams across to be able to produce these teeny tiny rotation curves, where you can basically measure your V out, because they are, you cannot say it's like, does it reach the flat part yet or not, but you can measure its V out and basically look at their dark matter halo profiles. And here and for this we managed to measure the resolved H1 kinematics of 67 galaxies. And if you are not very impressed with the number, the largest database of H1 rotation curves for spiral galaxies at redshift 0 right now contains something around 175 galaxies, and these observations were taken over the period of 30 years. So we're already kind of doing very well in this aspect. And here you see the multiple rotating phases of our galaxies, and they're all different, and some of them are very big and some of them are tiny and barely resolved. And we can also look at how our derived W50s match our V out, and we find them to be an excellent agreement if corrected for instrumental broadening and random motions of W50s, and corrected for the same inclinations. And here you see the typical error bar due to the velocity resolution, this 44 kilometers per second, and you see that our scatter is already much smaller than the error bar suggests. So we're also doing pretty great there, probing the new redshift space, which was never done before. And we finally can look at the Tully-Fisher relation from redshift 0 to 0.083, as you see in this bar, based on the rotation curves. And you see, you see it here, and with the black line, you see the redshift 0 relation from the database I mentioned, and they are free sigma borders. And you see that all our galaxies do scatter around the 0 redshift and all within the scatter, even with our bad velocity resolution. So we already can do pretty accurate job here to be able to say that over the last 1 billion years, we don't see the evolution of the Tully-Fisher, and it's pretty much scattered throughout the redshift 0 line. And if you will look at the simulations, because now also with the interest and with our ability to do it, the simulation started to look and these sort of things, and also based on different velocity measures. And here you see the examples of SIMBA simulations, and one based on the V flat, the same as here, and another one based on W50. And you see that here they do expect some evolution between 0 and 0.5 and 1, but of course they have much larger scatter than we have. And we cannot probe those parameters yet, so they would need to adjust to our parameters. But what we see is the striking difference what they have between V flat and W50, where the slopes change completely and the scatter increases a lot. However, if we look at our observations and the comparison W50 and V out, we see that V out W50 indeed has it's a larger scatter, but it is still within the free sigma. So the simulations still need to do the adjustments and check how they relate and if we actually derive the same measured properties. But what we confirm as well within this redshift range is that rotational velocity from the rotation curve will give us a tighter correlation than W50, where you see the galaxies are more spread. So this what we can conclude for now. Finally, for the first time, based on the H1, we can measure the evolution of the TFR over the 1 billion years. It's not a lot, but it's already a big step for us. And we see that there is no evolution. And another study, which is supposed to be submitted very, very soon, looked at the galaxies at redshift 0.2, but in a very small volume of a cluster. And it's called bodies of two clusters, basically, Abel 963 and Abel 2192. And they found that the galaxies also consist with redshift 0 based on the luminous R-band Tully-Fisher relation. So we can say that for now, we don't see observational evidence when comparing H1 at redshift 0 with H1 at further redshift of the evolution Tully-Fisher relation all the way to 0.2. And basically, what does it mean for now? For now, it means that we can apply independent calibrations, which we used before for the distance estimates, all the way up to this redshift, and be sure that our calibrations will hold since there is no evolution. And of course, theoretically, the evolution of the Tully-Fisher relation will suggest you that there are different scenarios of the halo assemblies histories, that the halos experience different assemblies of histories and they acquire different amount of baryons throughout their evolution. And this is something which we can trace as soon as we will find that indeed galaxies do change their slope or the scatter on the TFR. And since we left sort of the big to fail and the dwarf things, now we can back to them and to see what about my TH1 as a survey and the dwarf galaxies. And as I already told you, the important things to study dwarfs in H1 is to have N resolution and sensitivity. And it's something which previous instruments never had. You either have very good resolution with interferometer, but very low sensitivity, so you cannot detect diffuse H1, or you have great sensitivity, but very high beam of a single dish telescope, and you basically will miss on your dwarfs. So now we are finally on this regime where we can have both with Meerkat. And for example, one of the outcomes of it is that we managed to detect this galaxy, which was known, it was observed before, but for the first time we found that it has a companion which we would finally resolve. And therefore we plan to find many more companions within the MyTH1 survey and many more dwarf galaxies. And here, and of course, to be able to study their kinematics, they must be resolved. So here is the example of how many galaxies of H1 mass we expect to be resolved within 1 beam, 3 beams, and 5 beams. So for redshift 0, we expect to have around like 50 resolved galaxies below 10 to the 9, which is already comparable to the general samples we have of dwarf galaxies. And of course, with our new software and techniques, we are able to not just measure one number for their rotation, the width of the profile, but we are able to construct the rotation curve and check where they are light in the too big to fail relation, or in the baryonic Tully-Fisher relation. And as I've told you in the beginning, baryonic Tully-Fisher relation is supposed to hold for all types of galaxies. However, again, very exciting time for all of us, because recently the entire group of ultra diffuse dwarf galaxies been observed, and they kinematics studied, and they showed that they are extremely H1 rich, and they are extremely off the Tully-Fisher relation for the first time, and they are more closer to the relation predicted by the lambda CDM. So somehow they think that they were able to have all their baryons hold. And of course, we're very excited that we will be able to find more of these galaxies and study them in more detail. So basically, this is how all of it comes together: resolved kinematics, Tully-Fisher relation, and the dwarf galaxies. And in comparison, you will see all dwarf galaxies of very similar masses, but not being ultra diffuse and gas rich. They do lie on the TFR. So indeed, this is a separate group of the galaxies, which is very exciting. And here I arrived to my conclusions. And basically, it is that imaging H1 in galaxies, its morphologies and kinematics, reveals a huge wealth of information which we will not be observed other way, and which sheds light about the formation mechanisms and transformation mechanisms of the galaxies. And the future blind surveys, such as Meerkat, with escape pathfinder such as Meerkat and ASCAP and Aperitif, will provide finally us with unprecedented amount of the H1 data cube across different environments, which will have n resolution and sensitivities to do this sort of studies. And pathfinders already now are pushing H1 detections beyond redshift 0 and allowing us to study its resolved H1 kinematics. And for now, we can see that for sure there is no visible evolution of the TFR over the last 1 billion years. So please stay tuned for our further studies. And I will stop here. Thank you.